Okay, hi everybody. So today I want to talk about the last subject in our discussion of real gases, the virial equation. So here I'm showing you the same data set, pressure versus 1 over volume for carbon dioxide, ideal gas behavior up here, real gas behavior up here. And the question is, if I gave you this data set, how would you fit it? First thing you might guess to do is just fit it to a straight line. Okay? And it works, you get something, but it's not very good. There's clearly some curvature in this line, which we're not accounting for. So maybe you would look at that and go, well, a straight line isn't very good. Maybe I can go to some sort of quadratic equation. If you go to a quadratic equation, you'll start to notice that this fit is looking really, really good, right? This is essentially what we do in the virial equation model. Right? So the virial equation uses a power series, right? A quadratic expression. And the way you usually think about this is we have some variable. Right? It's written as a function of something, right? Which are to different powers. So this would be the 0th power. Here's the first power, the second power. And these higher order terms are usually considered corrections on this ideal behavior. So you can see this most clearly if I take that CO2 PV data and plot it as Z, the compression factor, versus 1 over Vm. What we would expect is that if we had an ideal gas, the compression factor would be 1 at all volumes. In fact, we have non-ideal behavior, and we can capture that here. So the 0th order term is 1, and then we start to see these corrections, which account for non-ideal behavior. And depending on what level of accuracy and precision we want to calculate our answer at, we can do a first order correction, a second order, a third order, blah, blah, blah. We can use whatever power we want in order to get as an accurate and precise of an answer as we want. So that's what we do. Here is formally how we write the virial equation. PVM equals RT times this polynomial, 1 plus B over Vm plus C over Vm squared. This is our power series. It's written in powers of 1 over Vm, so that's the equivalent of the x variable. And these coefficients that are here are called the second and the third virial coefficients. These are some constant that you look up for a gas, and they're correcting for real behavior in the gas. Give me 1 second. All right. So one quick note, you may sometimes see this written in a slightly different form. This is the virial equation, which is written in a power series in terms of the pressure P rather than 1 over V. These constants are slightly different. If you look at them, they'd have to have different units. And so you'll see these virial constants written as B prime or C prime in order to differentiate that these are different than the virial equation written in powers of 1 over V. So just like the van der Waals equation, the second and third virial coefficients are parameters that you look up. They're shown here for different gases. Right? Again, small inert things have small corrections. Big things with lots of electrons and intermolecular forces like CO2 and xenon have much larger virial coefficients. It's also important to note that these are functions of temperature. So at different temperatures, the virial equations can have different values, and that might make some sense to you. Gases are interacting differently at different temperatures. And one of the great things about this model is because it's effectively just a fit, right? We're just fitting the data. The virial equation works really well. It is the best description of gas behavior. However, one of the downsides of it is that we don't have a real specific meaning of what the coefficients mean. Right? Van der Waals coefficients were telling you something about the size of the molecules or the strength of the interactions. Here, these are just sort of empirical fits, and they are what they are. So that's what I have for you on real gases. There's some sample problems where you can calculate some things and use it. But I want to take one step back and kind of look at the big picture. So we've looked at these two different models. One I called ideal gas law, and the other I called real gas equations. Real gases would include van der Waals and the virial equation. One of the strengths of the ideal gas law is it's universal. It works for every gas, right? I don't care what the identity of the gas is. I can just plug my pressure and temperature in and get volumes. The problem with this model is that it has limited accuracy. Unless you're at really low pressures, the molecules are really far apart, this model actually doesn't work very well. In contrast, the real gas equations are broadly accurate. Right? They're very, very accurate in a number of conditions. But the penalty that you pay is that they're gas specific. So now you have to go look up all of these constants. They might be temperature dependent. You have to put in a lot more work to get it to go. And so the question you might ask is, is there a way to combine these two features into a single equation? Two features, I mean something which is universal and accounts for the fact that molecules can interact. And I guess in a preview of coming interactions, I'll tell you that the answer is yes, you can. And here's how you might think about that. This is a phase diagram for carbon dioxide. It involves solids, liquids, and gases, so it's different than what we've talked about, but I suspect that you've seen these things before. And on phase diagrams, there's often this point up here called the critical point, which is identified. Now, exactly what the critical point is hard to define. Sometimes people say, well, there's no boundary between the liquid and the gas. It's a single fluid which has the same density. And that's one way to think about it. It turns out you can actually use gas behavior to think about the critical point as well. And so here's an example of that. Again, this is PV data for carbon dioxide with theoretical predictions from the van der Waals equation at different temperatures. So as I increase the temperature, right, the pressure goes up, 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 up. And you can identify an important point on here. The important point is right here. Right? And this is actually the critical point of the gas. When you talk about this in terms of gas behavior, the way we define the critical point is it is the temperature at which the slope never goes negative. So if I look at lower temperatures, you'll find that the slope actually turns over and goes negative there, and that's problematic. Furthermore, it will turn out that the first and second derivatives of this prediction are 0 at the critical point. So I can actually use this definition then to calculate what are called the critical pressure, volume, and temperature. Right? The pressure, the volume, and the temperature that are associated with this critical point. And here's what that looks like with the van der Waals model. Again, this is the pressure at the critical point, the temperature at the critical point, and the volume at the critical point. You get some equations. You can plug things in and calculate things. There's nothing too exciting about this. This is sort of as you would expect. Specifically, we see that it's gas dependent. So if a different gas has a different B parameter or a different A parameter, they'll have different critical points. However, it gets a lot more interesting if you start to calculate what's called a compression, not what's called, the compression factor, if you calculate the compression factor. And if you calculate the compression factor at the critical point, you plug all of these definitions in, and what you will find at the end of the day is that it is constant. It no longer depends on the specific gas. The compression factor at the critical point is the same for every single gas. And it's a really interesting observation. You can do some more math with this, and you can ultimately show how to do this. I'm not going to go into that, but if you want to read more about it, check it out here. So this idea is called the principle of corresponding states. It's in Atkins 1cc. And this is just a quick example of it. What you're seeing here are different gases. You're seeing P and now the compression factor. And even though you have different gases, they all fall on the same theoretical line. So you'll have to take my word for it at this point, but it is in fact possible to include a universal model which accounts for real gas behavior in systems. All right, I will stop here. Excuse me. I will see you next time, and we'll talk about kinetic theory of gases.